Your brain is a masterpiece of balance, a constant dance between neurons that excite and neurons that calm things down. Get that balance wrong and you can tip into seizures, autism, or worse. But new research shows the lines between these brain cells are far blurrier than we once thought. Today, let's explore how your brain keeps harmony between go and stop, and why understanding this balance could unlock new treatments for neurological disorders. Back in the late 1800s, Santiago Ramon y Cajal's stunning drawings revealed neurons for the first time, branches and webs that looked almost alive on paper. Since then, scientists have tried to classify these cells in endless ways, by shape, by location, by function. But at their core, most neurons fall into two groups, excitatory and inhibitory. Excitatory neurons mostly release glutamate, which lets positive ions rush in, raising voltage and sparking the neuron to fire. It's like pressing the accelerator. Inhibitory neurons release GABA, which lets negative ions flood in, lowering voltage, preventing firing. It's the brake. Together, they create the rhythm of your brain, the electrical symphony behind grabbing an apple, humming a tune, or remembering where you left your phone. The ratio between excitation and inhibition is critical. Too much excitation can cause epilepsy. Too much inhibition or too little excitation links to conditions like autism. Interestingly, as mammalian brains evolved, inhibitory neurons became more diverse and abundant. That suggests inhibition isn't just about control, it's essential for higher thought and complex memory. For years, inhibitory neurons were seen as background players, a blanket layer of suppression. But large mapping projects, like the Microns project, show something new. These cells are highly specific. Some target dendrites, others cell bodies, and they often form precise partnerships with select neurons. Inhibitors aren't just brakes, they're fine-tuners, sharpening important signals and filtering out noise. In fact, recent work in mice shows they actively help with rapid learning and memory. Here's the puzzle. Neurons fire in milliseconds, but our thoughts and behaviors unfold much more slowly. How does lightning-fast signaling create long, drawn-out experiences? The answer may lie in a third, often overlooked group: neuromodulatory neurons. Neuromodulators like dopamine and serotonin don't just jump across one synapse, they can flood entire regions, changing how excitatory and inhibitory neurons behave. They work on slower timescales, creating an emotional and motivational backdrop. That's why a surge of norepinephrine, for example, makes emotionally charged memories far more likely to stick. And here's where things get even stranger. Some neurons don't stay in one lane. A few can release both glutamate and GABA. Others switch roles under stress, excitatory becoming inhibitory. The brain isn't just balanced, it's flexible. Our brains are constantly balancing push and pull, acceleration and braking, fast sparks and slow tides. Understanding how that balance is struck could transform how we treat seizures, autism, memory loss, and more. In the end, harmony in the brain may be the key to harmony in life.